Hello class and welcome. So we are in week 7 and this week and the next week we'll do chapter 8, which is mostly concerned with amplifiers. So we are in the field of analog circuits. Another chapter we have is frequency response. So chapters 8 and 9 are both dealing with analog circuits, amplification and so on. Um, so for the moment, you can kind of forget uh, digital stuff. Keep it in the back of your mind. So let's focus on analog. All right. So this chapter, let me expand this, is chapter 8 from the 6th edition of the textbook. And this chapter has 6 topics. Mostly, I'm going to cover 1 and 2. Maybe a little bit of 3, not too much, because again at NAU the emphasis is on MOS devices, not so much BJT, and this is more, item number 3 is more BJT. So I won't go too deeply into it, a little bit maybe. Then we've got 5 and 6 topics. So that's the plan for this chapter. Okay. All right, so let's start by looking at something called a differential amplifier. What is a differential amplifier? So, so far we have seen amplifiers with like one device, right? NMOS, PMOS device, or NPN or PNP BJTs. But if you take two of them and connect them as shown like this, then they form a differential pair. Okay, and that's what we're going to study here. So there are two main reasons for using differential in preference to single-ended amplifiers. So if you only had one device, then we can call that a single-ended amplifier, but you have two like this, it's called a differential amplifier. So here for the differential amplifier, the input is on the two bases of these NPN transistors, or on the MOSFET side, they're on the two gates on the NMOS side. So the output then is collected also across the two collectors or the two drains in this circuit. So such a connection, and the V output can be shown to be some gain factor, A differential, times the V input, which is the two signals between one base and another base, or one gate and another gate. So V out is gain times V in, right? So we can get the same benefit or the same behavior from a single device. So why have a double device? So the big advantages are, first, differential circuits are much less sensitive to noise and interference than single-ended circuits. Secondly, the differential configuration enables us to bias the amplifier and to couple amplifier stages together without the need for bypass and coupling capacitors. Now you may remember from previous amplifiers we have studied, such as the common emitter or the common source, that we have all these coupling capacitors between stages, right? First stage and the second stage, the output of the first goes as the input of the second amplifier, but in between you need a capacitor. And we know all these capacitors, etc., are difficult to make on ICs. So is there a way to eliminate those capacitors? And the answer is, if you use differential circuits, then it's easier, then you don't need the bypass and coupling capacitors. So these are the two big benefits. less sensitive to noise. So if you have a small signal coming onto the input, but that signal is being thrown back and forth because of some noise, that means some heavy DC level is shifting the little signal, then if you have a differential configuration like this, you can easily eliminate that noise and only focus on the signal of interest. So that's one of the big advantages of having a differential configuration. Then of course the second benefit is you can get rid of coupling capacitors. So let's see how all this is done. Make sure you become familiar with how the two are connected, right? The two collectors are connected in this case, and then the emitters are connected also in this way. Similarly here for the NMOS devices, the two drains after the drain resistors are connected, and the two sources before the biasing resistor RSS is connected like this. Okay, so here's an example of an actual IC, which is a Texas Instruments THS4130 fully differential input output low noise amplifier. And this Q1 and Q2 forms your basic differential pair. The other transistor pairs here help with increasing output impedance and stuff like that. These symbols talk about current sources. So all that put together in an 8-pin package from Texas Instruments looks like this. And you can buy this for a few dollars. The benefits are high performance. So 150 megahertz minus 3 dB bandwidth. Then there's stuff called slew rate and harmonic distortion. We'll study this later. But low noise is mentioned here. And then differential input, differential output. Balanced output rejects common mode noise. Second harmonic distortion is reduced. Wide power supply, the same device can operate from 5 volts all the way to single supply, all the way to plus or minus 15 volts dual supply. That means both plus and minus can be connected if necessary. So I just wanted to show you what a real differential circuit looks like. I mean, there's a lot more complexity here than we're going to study, but at least if you understand the basic principles of a differential pair, how they are connected, why we have current sources, that should be good enough for now. Okay. All right. So let's proceed and talk a little more about all the currents and the voltages in a basic differential pair. So we have gone to a MOS differential pair first, because that's of more interest in today's technology. So it consists of two transistors, Q1 and Q2, both are NPN in this case, whose sources are joined together, right here on the bottom there, and biased by a constant current source I. So this constant current source I is what is setting the bias point for the two transistors. Now, one important thing is as we operate this device, this differential amplifier, neither of the MOSFETs should enter the triode. So it's okay for the for the differential amplifiers to be in the cutoff region or in the saturation region, but they should not enter triode. Okay. So let's look at 8.1.1, which is operation with a common mode input voltage. So a differential amplifier has two types of, or you can put the input signal in two ways. One is through a method called the common mode, and the other is the method called differential input. So let's see what the difference is. The two gate terminals are joined together and connected to a voltage VCM called the common mode voltage. So common mode voltage means this voltage is going into the into the gate of Q1, but it's also going into the gate of Q2. So the exact same voltage is going as the input for both the devices in the pair. Because the same voltage is going, and because of the fact that Q1 and Q2 are matched, and as long as they remain in the saturation region, the current I will divide equally between the two transistors. So this I is I by 2 here and I by 2 here. And we know that there is no gate current in a MOS device. So the I by 2 goes all the way from the source to the drain, or the reverse, right? It comes down from the drain through the transistor into the source and then goes out. But the important thing is that this I is divided equally between the two. This is only true for common mode signal. Okay. So how will the current divide? So the I by 2 is in each device, and then the corresponding overdrive voltage can be found using this formula. Also, the voltages at the drains, this voltage VD1, VD2 is equal, and it's VDD minus half IRD. Half IRD. Okay. So one thing, and this is shown clearly in the textbook, so you should read it also. But as you change VCM, you can have it at a low value, 0.1 volt or 0.2 volts, or you can have a high value like 1 volt, 1.5 volts, whatever. What you'll notice is none of that appears in the output. The output is always going to be fixed like this. So the magnitude of the common mode voltage has no impact on the output. So what we say is the differential pair does not respond to common mode input signals. That is, it rejects common mode input signal. So you can have a flat plus 1 volt, you can have a signal on this plus 1 volt plus or minus 0.1 millivolts or something. You can do whatever you want with VCM, but none of that comes to the output. So what we are saying then is, because the output is not impacted by the input, we say that the transistor pair does not respond to common mode input signals. Now, this cannot happen forever, right? It can't, let's say you put 20 volts here, you can't say, okay, even now it's rejecting. So for a certain range of common mode signals, there is no impact, there's no effect on the magnitude of the common mode signal. It doesn't appear on the output. So what is that range that it can handle? That range is an important specification. An important specification of a differential amplifier is its input common mode range. That is, what is the minimum and maximum values of the common mode voltage. So for an NMOS device, we can say what is the highest VCM that it can work with and still reject it. That is found using this formula. It depends on VDD, it depends on VT, and it also depends on the biasing current and of course the drain resistors. Similarly, what is the lowest VCM it can handle without going into cutoff or something? That depends on the needed voltage across the current source. So across this current source, a certain voltage has to be maintained. Otherwise, the transistors in this current source may not work. So that voltage, VCS, kind of determines what should be the VCM minimum. And that has this formula. So the bottom line is, we can say in general that a differential pair rejects common mode voltages. But of course, the common mode voltages has to be within a certain range, a certain minimum and a certain maximum. So we'll do problems. There's a nice example on finding the highest value, the lowest value of VCM and all that. But we'll come back and look at it in my next recording. So let's move on to 8.1.2. Remember, 8.1 is the subject of MOS differential pair, the basic introduction. So 1.2 talks about the other kind of input voltage, the differential input voltage. Remember, I said there's a common mode input voltage and there's a differential input voltage. We just saw that common mode is rejected. Differential, obviously, we want it to be amplified. So, the differential mode, what that means is, it is only applied to one of the two devices and the other is grounded. Now that's one way of doing it. Another way of doing it is, of course, to apply it to both inputs, that means both gates, but not equally, right? If you do it equally, then it's common mode. But if you put more into one and less into the other, then there is a differential, there's a difference between the two. Let's say we put 2 volts on Q1 and 1 volt on Q2, then the difference is 2 minus 1 or 1, right? That's the effective input signal going into the differential amplifier. So you can do it either way, but once you put in a differential input, that means the inputs are different between the two devices on their input terminals, then you get amplification. So with ID positive, ID is the differential input to the whole thing. Here what we have shown is one of them is set to kind of a reference or ground, one of the inputs, and the other input is shown as VI differential, V input differential. So if VID is positive, as shown in this configuration, then VGS1 is higher than VGS2, right? Because this is going right here and this point is common to both. So this higher voltage makes VGS1 higher. That means this drain current is higher than ID2. And because of that, because the drain current higher than here, this voltage, which is the difference between VDD and this, the more the current, the less will be the voltage at this point. So what you get is VD1 will be less than VD2, and thus the output VD2 minus VDN. See, we define the output voltage as the difference between the voltage at this terminal and this terminal, VD2 minus VD1. So what you need to remember is, with ID positive, the output voltage will be positive. With ID negative, that means if this is turned around and the voltage going into the gate is a negative, then the output also will be negative. So there is no phase shift, there is no sign change in a differential input amplifier in this configuration. So the value of VID that causes the entire, so that is, with regards to the input voltage and how it affects the output voltage. Now, in common mode, we saw that the currents in the drains are equal. In the differential mode, we saw already that the current currents will be different. In the common mode, the currents are equal. Sorry, I should rephrase that. In the common mode, the currents in the two devices are equal and they're half of the reference current. In the differential mode, the currents are always different, and it's possible that we can make, by suitably biasing the devices, all the current just flow in one and zero in the other, and vice versa. So, one thing of interest then is the value of ID that causes the entire bias current I to flow in one of the two transistors. So, entire bias current I is steered into Q1. If you want that situation, then VID should be root 2 into V over drive voltage. Entire bias current is steered into Q2. If you want everything to go into Q2, then your bias current should be negative. Sorry, your input voltage VID should be negative, and its value should be minus root 2 VOV. So this derivation is in the textbook. It's not very difficult, but take a look at it. But the bottom line is this VID can be this limit, root 2 VOV, or it can be minus root 2 VOV to make your current entirely in one device or entirely in the other device. And any value for VID between these two, the current will split in some proportion between the two devices. So it is assumed here that both Q1 and Q2 remain in saturation even when only one of them is conducting the entire current. Okay. Okay. Next we study amplification, or using this as an amplifier. Now obviously that's the goal, right? We are talking about analog electronics, which is all about amplification. So what more can we learn about the amplification behavior of this pair? Remember, the output voltage is still this, the input voltage is still the differential input ID, VID. So if the differential input signal VID is small, that's an important requirement, then the current in one of the transistors, let's say Q1, when VID is positive, we know that when VID is positive, more of the current flows here. The current will increase by an increment delta I proportional to VID. So in common mode, if you assume that they are equal, then in differential mode, the current here in one of the devices will be higher by a value I by 2 plus delta I. Actually, maybe I should write this as delta I instead of I delta. So let's call that delta I. Okay. So if the current that was flowing when we had common mode signal is I by 2, then by applying the differential voltage to one of the devices, you have increased the current by a factor delta I. Because of this VI delta. So this delta I is proportional to VID. Then the output voltage taken between the two drains, that is this voltage VD1, VD2 minus VD1, will be twice the delta I and RD. So this product 2 delta I RD gives you the magnitude of the output voltage, which is proportional to the input signal, right? Because delta I is proportional to VID, we can say the output is proportional to the input. And of course, we'll do a lot more on the small signal analysis to understand the gain and so on. But for now, just remember that the change in the current over what would be true in a common mode situation, that delta I is part of the expression or the formula for the output voltage, which is 2 delta I times the drain resistance. Okay. All right, some more theory. So we have large signal operation and then we have small signal operation. The small signal operation, I will do it in a next or a separate recording. But let's study a little more about large signal operation as shown in this slide. So there are, we still, whenever we have these devices, MOSFET devices, obviously we only have one or two formulas that we can work with, right? The same thing keeps appearing again and again. We are interested in something called the overdrive voltage, which is always, the gate to source voltage plus the VT, the threshold voltage. Then we have a formula for drain currents, right? ID, which is generally half, and then it depends on this Kn prime, W by L, and so on. So the same voltages, if you keep flipping them around, is what you see is happening in all these analysis. And much of this is again in the textbook. So please read through it so that you understand how they are derived. But for our purpose of being able to actually use all these formulas in some problems and take exams and so on, let me focus on the actual formulas. So the expression for the drain currents ID1 and ID2 in terms of the differential input signal VID, which is the difference between the gate signal VG1 minus VG2, right? So ID1 in terms of VID is this, and ID2, this plus changes to minus. Everything else is the same. Now if you want to rewrite that in terms of overdrive voltage, remember if I is constant through a outside current source for biasing, then this I will force the two devices into operating with a certain overdrive voltage, right? Now remember here we are got two different signals, VG1 and VG2. And VG1 is not equal to VG2. If they were, then they would be common mode and they would be rejected. So assuming VG1 and VG2 are different, and the input is the difference between the two, then the overdrive voltage for the two devices will be the same, and that overdrive voltage, that is determined by I basically, because WIL is the same, right? So overdrive voltage stays the same, and the formulas for ID1 and ID2 are given here in 8.23 and 8.24 in the textbook. So basically the ID, which is the difference between G1 and G2, determines what is ID1 and what is ID2. And if you add the two, you should get I. That's why there's a plus and a minus. Okay. Now, now remember this is a square formula, right? You've got a square root and then you've got a square. So it's definitely not a linear relationship. It's not like a straight line relationship. It's more like a square relationship. But you can approximate it to a linear relationship. Remember, when we are studying amplification, we like linearity because only linear behavior of an amplifier gives you fidelity. That means the output waveform, if it must be similar to the input waveform, just of higher magnitude and no other changes, no other distortions, for that to happen, you need linearity, right? That's the definition of linearity. The output is similar to the input, only difference is the magnitude is different. So for that to happen, it's possible even in here, even with all these square formulas, still possible to make it linear, assuming your input signal is small. So if your input signal is small, that means the VID or half of VID is much less than the overdrive voltage. Then these formulas can be simplified to look like this. So ID1 will be linearly proportional to VID, and ID2 also will be linearly proportional to VID. And we know that once the current changes are linear, then the output voltage will be linearly connected to the input voltage. So the amplifier is operating linearly. But for that, obviously, you need small signals to eliminate the impact of the square and the square roots and all that. Okay? All right. Here's a little more on the large signal operation. So these graphs, they are what is called normalized plots of the currents in a MOSFET differential pair. So as you try to understand these, let's look at the center. Here, VID at this middle is 0. That means it's in the two signals are equal, so it's common mode operation, and in common mode operation there is no VID, but the currents are exactly half of the bias current I, the currents in each of the devices. Now we know that as you go in one direction or the other, that means as VID goes towards root 2 times overdrive, which is 1.4 times overdrive, or it goes to minus root 2 times overdrive, then the current switches from one device, Q1 in this case, to the other device. So if the current, Q1, if this is Q1, then it's falling to 0 here, right? When you're at root 2 VOV, and it's high when it's minus root 2 VOV. So that should be behavior of Q. So this is the behavior of Q2 and this is the behavior of Q1, right? That's why we call it ID1 and ID2. So this graph is the behavior of Q1, this graph is the behavior of Q2. But the bottom line is the current, as we have already seen, can be all in one device or all in the other. And these graphs help you track based on this ratio VID by VOV where the current is splitting, how it's splitting. How much of it is in Q2, how much of it is Q1. Because that determines the output voltage, the gain. The ratio of the output to input is determined by also the current split. Now, again, this is a nonlinear relationship. Well, it's linear in certain portions, and then it becomes nonlinear here. So this graph tells us that as you increase the overdrive voltage, so let's say the overdrive voltage is 0.2 and that is the graph. It is linear up to this point and then it becomes nonlinear and it kind of flattens out. Compare that to this graph with VOV is 0.4. It's almost like it has a much higher range of linearity, right? It's from here to here you can say is linear and then it starts to curve and flatten. So this graph tells us, and this is in terms of VID directly, not the ratio, the lower scale axis. This says that the linear range of operation of the MOS differential pair can be extended by operating the transistor at a higher value of VOV. So the higher the overdrive voltage, the more linearity you can get, and thus you can improve the behavior of your transistor for a higher range of input signal. Okay, so that's an important lesson to learn from these graphs. More overdrive voltage, the better, and that means the higher the biasing current, obviously, the better amplifier performance you can get out of the pair. Okay. All right. I've got many problems that we'll come back and look at. So you can see some of the problems that are listed here. Exercise 8.2 says, find the value of VID, the input voltage that causes Q1 to conduct, and the corresponding values of VD and V2. Similarly, find the value of the input that causes Q2 to conduct the entire current. So that's some of the formulas we saw. So we have to use those formulas. Here is an example of a PMOS device. Now generally we don't talk too much about PMOS or PNP transistors because it's easier to just stick with NMOS, understand the theory, then the PMOS becomes easier. But what you'll notice is with the PMOS, the circuit diagram also looks reverse, right? Compared to, let's say, an NMOS, here you'll see NMOS, the sources are connected to the current source, the biasing source. The source of the two Qs are connected to the biasing source, current source I, and the drain resistors are connected to the plus VDD. For a PMOS, it's opposite. The sources are connected to the plus VDD, well, this Vs in this case, and the drains and the two sources are tied together. For the PMOS, you'll also see the sources are tied together, but the positive voltage is by the drains. Here, the positive voltage is by the sources. I think you'll remember this. I think I said previously one time that in an NMOS device, the positive is on the drain and the current flows from drain to source. With a PMOS device, the positive is on the source and the current flows from source to drain, which is the opposite of the NMOS. Anyway, this is an example with a 0.5 milliamp current source, and then we have to find pretty much the same thing. Find the overdrive voltage and the source to gate signal and all that. Okay. All right. So we have another 5 minutes. And like I said, the BJT examples or the BJT case of this differential amplifier, we'll talk briefly about it. Probably don't have too many problems, but instead of totally neglecting it, I thought I will at least take maybe 5 to 10% of the available time to look at the BJT also. Because you can certainly not say that BJT differential pairs don't exist anymore, right? They're still there, they're used quite a bit in analog electronics. So I feel you should be at least aware of the similarities and the differences compared to the MOS differential pair. Okay. All right. So looking at the drawing first, the circuit drawing of a differential pair made up of two NPN transistors. Same definition. The differential pair consists of two matched transistors Q1 and Q2 whose emitters are joined together. For a MOS device, we said that the two sources are joined together. So correspondingly, for BJTs, we say that the two emitters are joined together and biased by a constant current source, I. Also, these are high beta devices so that the output resistance can be ignored for the moment. And based on that, we'll do a little bit of analysis to understand what's going on with the BJT. The important condition, remember we had a similar important condition that MOSFET should never enter the triode region. So the corresponding condition is that the two collector currents should not allow Q1 and Q2 to enter saturation. So these devices need to be primarily operating in the active mode, and they may be in cutoff occasionally, but between active and cutoff, but not saturation. Okay, so again, as we study the BJT pair, the first mode of operation is common mode. Common mode, similar to what we saw for MOSFETs, we take the two input terminals, which in this case are the base terminals. The two base terminals are tied together, and one input voltage, VCM, is applied to both the bases. So the same base voltage applies to both. Hence, you expect that if the similarity is true between BJT and MOSFET amplifiers, differential pairs, then everything that we learned from MOSFET also applies here, which is true. So what will happen is the current I is split half and half between the two collectors. Now, obviously, we know that compared to MOS devices, the collector currents are not exactly identical to the emitter currents in a BJT device, right? Because the base current also exists, a small amount. It's very small, maybe 1%. Because we know alpha, this parameter for a transistor, is about 0.98 or 99. So if this is 1 amp here, then if you add these two currents in these two collectors, the current won't be exactly 1 amp, but it will be, let's say, 0.99 amps, depending on alpha. So that 99 is then divided into 2 equally. And the remaining 0.01 amp, the 1%, is flowing in the base currents, the bases. Because we know that in a BJT, the emitter current equals the collector current plus the base current. While in a MOS device, because there is no gate current, we generally assume that the same current flows through the drain and the source. Here there's a slight difference. Anyway, with that caveat, we can say that the common mode operation, you apply this signal and the current will divide equally between the two devices. The voltage at the emitters is VCM minus VBE, right? The voltage at this emitter is VCM minus VBE, and VBE is generally about 0.7 volts for a transistor in saturation. So that will be VCM minus 0.7. The voltage at the collectors is VCC minus half IRC by KVL. So let me stop here and we'll come back and finish off the BJT and then look at some problems.